Well, this is the third of not 5 videos, but we're going to trim this to 4 videos on EAS, NAS reactions. And in the last 2 videos, we looked at the 5 different electrophiles you could use for electrophilic aromatic substitution. The halogen, nitration, sulfonation, alkylation, and acylation. We looked at those different types of electrophiles that were generated in Bronsted or Lewis acid conditions to be made more reactive, because we had to break aromaticity in that first step of an EAS reaction. So now what I'd like to do is look at what do we do if we have substituents or groups off of benzene ring before we make the attack of the electrophile. How does that group, other than some 6 hydrogens, what if we put a alcohol or a methoxy group or an amine or a methyl group off the benzene ring, how does that affect the reaction? So that's what we'll be looking at in this video. Substituent effects. So having something other than a hydrogen on all these carbons. So whatever Y is. Well, the first thing we probably want to do is just create 3 categories that we can, I guess, place this group into in terms of what it does. So sort of just to organize things. What type of classifications do we have? So we'll do that, I guess, in the bottom here. Let's remember what that group's going to do. It's going to either affect the reactivity of the benzene ring, and that's one issue. Does it make it more or less reactive towards this electrophile? It may, in other words, activate or deactivate. And then second, a separate issue, it may affect where the electrophile goes in reference to this substituent. So it directs the orientation, and we need to know what these positions are: ortho, para, and meta. The ortho position is the carbon next to the carbon that has that Y group off of it, whatever we're relating it to. We say this is at the ortho position relative to this Y group. We have 2 carbons away, 1, 2 from this position. That's the meta position to this Y group. And if we're right across from the Y group, we say this electrophile is attached to the carbon that's para to this position where the Y group is. So ortho, para, and meta relate positions to each other. If we're next to, 2 steps away, and across from Y, we're ortho, meta, and para in that order. Ortho, meta, and para. I put these 2 together because we'll find some of our activators direct things to the ortho and para positions. So let's get to those 3 categories that you have for any Y group. We have what we call ortho-para directing activators. So I want to be very careful. We're not saying we have, I guess, ortho-para activators. We're saying ortho-para directing, and the group is an activator. So we need to keep that in mind, that we're talking about 2 different things: the reactivity, it's an activator, and the orientation, ortho-para directing. This first category is for those Y groups that have an atom in the Y group that bonds the group to the ring and has a lone pair. So the atom bonding this group, whatever, there may be more atoms behind Y, it might be a nitro group or amine or hydroxy group. If the atom bonded to this carbon has a lone pair, and this is excluding hydrogens, then this group is an activator. So the examples would be hydroxides, amines, methoxy groups. These have the atoms, these were Y groups, the oxygen, the nitrogen, and the oxygen in the OH group have a lone pair that connects the OH. The oxygen connecting the OH to the ring has a lone pair. And the halogens are moved over to this category of ortho-para directing deactivators because they still have the lone pair, but they inductively withdraw. So we'll leave them over here. So halogens are the only type of, well, not only, but they're the dominant type of ortho-para directing deactivator, meaning the ring is less reactive, but it's still directing the electrophile to the ortho and para positions. But let's go ahead and finish this category. We have the ortho-pair directing activators. That is, the best are the ones that have atoms bonding the group to the ring that has a lone pair. And the second type of ortho-pair directing activator that's not as strongly activating is having alkyl, aryl, and alkenyl groups off the benzene ring. Alkyl, just alkyl groups are, aryl, of course, other benzene rings, or alkenyl groups, a double bond and an alkene off of the benzene ring. We've already talked about halogens. They are the type of dominant type of ortho-pair directing deactivator. Then the last is a meta-directing, and I'm just abbreviating here, meta-directing deactivators. So the groups here and here overall withdraw electron density, but if Y is a halogen, it still directs the electrophile to the ortho-pair positions. And if the Y is involving a group that has an atom bonding the group to the ring that has a pi bond to electronegative element, such as the nitro group is one of the strongest meta-directing deactivators. The atom bonding the group to the ring has a pi bond to an electronegative atom. So there's the pi bond to the oxygen. And if this was on the benzene ring, this would be a meta-directing deactivator because the atom bonding the group to the ring has a pi bond to an electronegative atom. The last one is a trifluoromethyl group. You just want to know that for different reasons, this is also a meta-directing deactivator. It's not going to be a resonance thing. It's going to be just an inductive thing. Fluorines, we know, are very electronegative. It's pulling on this carbon. If that's attached to the ring, this is a very partially positive carbon, and thus it's going to pull significantly through inductive effects. So those are the three categories to keep in mind as we look at different Ys. Try to classify them as ortho-pair directing activators. Just know your halogens are ortho-pair directing deactivators. And the last and most deactivating type of group, meta-directing deactivators, where the atom bonding the group to the ring has a pi bond to an electronegative atom. So you say, well, are there any other types? Yeah, the carbonyl, where we have an atom bonding the group to the ring, this being my little ring, has a pi bond to an electronegative atom, oxygen, nitrogen. Alright, let's use that to classify a few. So we can say, okay, substituent effects and overview. My three categories: ortho-pair directing activator, ortho-pair directing deactivator, meta-directing deactivator. This would certainly fall into that camp because the atom bonding the group to the ring is bonded through a pi bond to a more electronegative atom, nitrogen. So that would be a meta-directing deactivator. We show an electrostatic potential map showing how the electron density is rich here, and we have a green color or yellow color indicating that we're in a blue at these hydrogens, indicating that the hydrogens would have significant partially positive charge around this benzene ring. So it's been deactivated. Please, that does not mean it cannot go through an EAS. It just means it's a slower reaction, harder to push into an EAS. The chlorine off of a benzene ring, halogens off of a benzene ring, those are the ortho-pair directing deactivators that I need to know. Then I put two in this category of ortho-pair directing activators in this order. More activating is the amine than the methyl, alkyl, aryl groups. In general, this amine does have a nitrogen bonding the NH2 to this ring, wherein the atom bonding the group to the ring has a lone pair and is not in a pi bond. So we're going to see here in just a little bit that the reason why this is such a strong activator is because it can give bi-resonance to the benzene ring. Alkyl group cannot do that. It gives a little bit by inductive effect, but this one's over here because it gives by resonance effect. It takes by inductive effect out, but it gives a lot more by resonance effect. So we compare or contrast these types of rings where we have orthopair directing activators of different strength, this one being the richest ring with electron density. This one we can see is yellow-green, meaning there's not as much electron density in the ring when we have a cyano group off the benzene ring. So nucleophilicity can be affected, of course, as these either donate, the ring becomes richer, the ring is more reactive with electrophiles. And we talked a little bit about that in terms of resonance and inductive effect. Let's talk a little about that a little bit more. So let's look at these substituent effects on the front side, how these Y groups affect the benzene ring on the front side. And then we're going to jump to the back side pretty quickly in the next few minutes. So just a quick review of resonance. Hopefully you know that resonance, we move electron density mostly through the pi bonding. We follow resonance forms to see resonance effect. In inductive effects, we just move through the sigma bonding. It's a difference in electronegativity that dominates or that controls this. This can be due to differences in atoms or hybridization. This little difference here is due to the fact this is sp3, this carbon's sp2. This carbon then pulls a little bit more since its hybrid orbital reaching out and overlapping with this hybrid orbital is a little lower in energy, so we have a slight donation of the sigma electrons to this carbon. So that would be an inductive effect. That's important again because we're needing to know how reactive this ring is. If this ring has a little bit more electron density, its reactivity goes up, and of course the energy of activation then overall goes down. So anything we can do to increase the electron density in this ring pushes the starting energy of the ring up a little bit. And if we take electron density out, of course, it lowers the starting energy, making these electrons less reactive with the electrophile, making the energy of activation higher. Let's start keying in on resonance. We said these amines can give by resonance. They take because they're more electronegative, N's or O's, than the carbon, but they give by resonance. Not just every carbon in the ring excess electrons, but really the ortho and para positions. If you draw the resonance forms for aniline, you notice that the ortho and para positions, when we draw resonance forms, can be drawn with full negative charges on them. And that's illustrating the resonance effect of the amine on the benzene ring. So in summary, we can just consider IE and RE when we try to consider on the front side, before we attack the electrophile, how this ring is affected. Whether we have increased electron density and the energy reactivity goes up, or we have withdrawing and the energy goes down. Sorry, they have these arrows. The arrows are indicating the energy of this thing. If we push in with electrons, the reactivity goes up. If we pull out with electrons, the starting energy goes down and we have a higher hill to climb. So inductive effects, resonance effects, this one as an OH group, it pulls out. Now my arrows are going to indicate which direction the electrons flow. Electron density is pulled out by the oxygen if we consider inductive effect, but there's a much greater resonance effect that gives to the ring. Methyl groups, they give slightly to the ring, and they have no resonance effect. There's no pi bonding between this carbon and this carbon, so there's just no resonance effect. Chlorine, we take out by inductive effect, and we give very little by resonance effect. So it turns out that it's a ortho-para directing deactivator because IE, in this case, very often this is not the case, it's usually the other way around, but in this case, IE trumps RE. This is a stronger taker by inductive effect than it is a giver by resonance effect, like we saw for hydroxyl groups. Now this one, IE and RE, pull the same way. So we can kind of see why these cyano groups, nitro groups, why they're strongly deactivating, whereas halogens are just weakly deactivating, because the arrows for IE and RE go in the same direction towards the group when we have nitro groups, carbonyls, cyano groups on the benzene ring. And that's the last I want to talk about the front side. I want to start talking about the back side, the sigma complex. How do the Y groups affect the back side after you've attacked the electrophile? Because really that's key. Whatever we can do to lower the energy of this is really going to dominate the reaction. Not so much the starting energy of the benzene ring, although we can look at that. Usually they go together. Whatever good for the front side is good for the back side. And whatever's bad for the front side, meaning it makes the ring less reactive towards the electrophile, also makes this thing less stable. So let's finish with this backside of issues and we'll be done. This is key. How do we affect the sigma complex with our Y group? So I'm not going to review inductive effects and resonance effects, but just to say now we're going to consider inductive effects and resonance effects for the backside, the carbocation, the sigma complex or cyclohexyldienyl cation, where we have resonance forms for this ring involving the carbons in the ring, but we also consider possible resonance forms added if this Y group can donate electrons, and it can. So if we put a positive across from a nitrogen that has lone pairs, we can gain an additional resonance form. The lone pair can drop down to a pi bond, and we can gain, just going to go ahead and draw it here, because of resonance energy, we can gain a resonance form that lowers the energy of this sigma complex, lowering the energy of activation, because if we lower the energy of the intermediate, we lower the energy of the transition state, we lower the activation energy. This sigma complex is more easily formed than others, and compared to others, talking about the nitro group. Put a carbon with positive right across from this, that would be very bad. There's nothing that the nitro group can donate to this carbon as a lone pair goes. So this would be very unstable. We would not see this favored as a sigma complex. So we have to consider resonance effect on the back side. Let's do that one more time. If we have a hydroxyl group and we want to attack the electrophile with our pi electrons, we can put it and these two are equivalent ortho positions. Let's put it, we're going to take and use pi electrons, but we're going to put it at the ortho position next to the OH. So we do that. We use these two pi electrons. We then leave the positive charge on the carbon connected to the OH. That's a good thing because we can donate down lone pair to pi and have an additional resonance form beyond just the two others that you get with any sigma complex, with any benzene ring. We can go ahead and donate pi electrons in the ring to the positive charge. That could have been done without the OH group. It doesn't matter. If we take the OH group off, we always have the sigma complex with two additional resonance forms because of the ring. Pi to pi, positive charge is here. Pi to pi, positive charge is here. But this is the additional resonance form that we get that makes this a good group to have on, an activator that lowers the energy of that intermediate on the back side. Just for contrast, if we put the electrophile here at the meta position and have the positive charge, of course, here at this carbon, if we use the pi electrons to attach the electrophile to the meta position, the positive charge, we can still move around the ring. We can still have pi to pi transition, putting the positive charge here, and then a pi to pi transition, moving the positive charge to here, but it never lands on this carbon. We can't make use of the additional resonance form if we attach the electrophile to the meta position. Moving right along, if we were to take the other type of ortho-para-directing activator that's just a alkyl group, it's not as activating, it's still better to put the electrophile, go ahead and use those, it's better to put the electrophile at the ortho or para position because the positive charge can at least land on the carbon that's connected to the alkyl group, and we would have a tertiary carbocation along with two resonance forms where we have secondary carbocations. But if we put the electrophile at the meta position, here, and we start off then with the positive charge here, we can go around the horn, around the ring to move the positive charge, but we never land on this carbon connected to the methyl group. So we have secondary carbocation to secondary, started from a secondary carbocation and go to a secondary carbocation. But we never make use of the tertiary carbocation that we can make use of if we attack from the ortho, or put the electrophile at the ortho or para position. We have just two more positions, or two more types of groups. Ortho-para directing deactivator to consider from a backside view, and the meta-directing deactivator. So let's finish with those two. The chlorine, we said, is not an activator, it's a deactivator. It doesn't mean we can't do an EAS when we have this term deactivator, it's just harder. But if we force it and push it, we're going to put the electrophile at the ortho or para position so that the positive can be across from the chlorine. And you say, well, that's bad. Well, no, it's not. When you're a carbocation, full positive charge on the carbon, that chlorine can give by resonance. It becomes a much different situation when it's a full positive. It can help. It can satisfy that charge by resonance. So we get an additional resonance form when we have the carbon with positive sitting right across from the chlorine. Of course, we can also get the others where we just do a pi to pi, put the positive charge here, pi to pi, put the positive charge here. But it's almost I don't know if this is a way to say it, that chlorine's not donating on the front side. This ring is less reactive in the beginning. But if you're going to force it and push chlorine or chlorobenzene into the dance of an EAS and say, fine, okay, you want to make me dance, I'll put the electrophile at the ortho or para positions, because then at least I can give by resonance. So it's not an activator, but if you force it, it directs the group to the ortho and para positions. Although the inductive effect reduces the reaction rate of the benzene ring, the ortho and para positions are favored due to the additional resonance form that is possible that we just saw. All right, the last is the meta-directing deactivators. We don't want to put the electrophile at the ortho or para position. If we do, the positive charge is across from a very partially positive carbon to begin with, and you can't by resonance give. There's no resonance form that can be drawn. We can't take the pi electrons down because that leaves O with only 6. So this is a bad sigma complex. This is something we want to avoid. So to avoid it, we don't attach the electrophile to the ortho or to the para positions. We want to avoid this one. So what we do is we attach the electrophile to the meta position. Attaching the electrophile at the meta position, we can go around the horn with any sigma complex. We always have the two resonance forms additional to the one immediately formed. This is just, well, we want to sort of avoid this one. So we do that by putting the electrophile at the meta position. Pi to pi, the positive charge would go here. But then again, we skip that carbon on purpose so we can avoid being with positive across from a partially positive, and we jump to this position. So that's why it's an avoidance thing. We put the group at the meta position to avoid the bad intermediate, the bad structurally, stability-wise, a very unstable intermediate. We avoid it by not putting this at the ortho and para positions, but by putting it at the meta position. So it's an avoidance thing. This group helps us. In this group, we want to avoid putting the electrophile at a position wherein we have a positive across from a partially positive. Ortho and para orientation is not favored because a formal positive charge is next to a partially positive carbon. We just want to avoid this. How do we do that? By putting the electrophile at a meta position. All right, we're almost done. Kind of a long video. But just remember those three categories: ortho-para directing activators, ortho-para directing deactivators, which are just halogens, and then the meta-directing deactivators, the strongest of the deactivators. A couple other things just need to finish up with. We talked about alkylation and acylation. Acylation. Those are types of Friedel-Crafts reactions, and you want to know that name. Friedel-Crafts reactions are alkylation or acylation reactions, where the electrophiles are an alkyl group or an acyl group. We need to know that we cannot have strong electron withdrawing groups like nitro groups, carbonyls, things that we're meta-directing deactivators on if we want to run these reactions. You can't have those on the ring and try to run a Friedel-Crafts reaction. And you can't have, this is interesting, we can't have electron donating groups involving the amines, and just an amine, a primary amine, a secondary amine attached to the ring. We can't have these amines. They're so strongly, I guess, donating that because of their lone pair can be used for protonation or binding to a Lewis acid. So you can kind of get it, they're just too good. They're too strongly reactive to donate to the ring that reactivity can be used towards the Lewis or Bronsted acids. They can react with the catalyst. So we tend to have to change their structure. We'll see, as you may see in class or whatever, to make a acetanilide or some sort of derivation of an amine. They're just too reactive with the catalyst. It's a catalyst issue. It reacts with the Bronsted or Lewis acid. So you can't have meta-directing groups on, so strongly withdrawing groups, meta-directing groups we can't have. And we can't have our amines, no amines, on if we want to run Friedel-Crafts reactions. That is alkylation or acylation. So meta-directing deactivators. We can't have meta-directing deactivators or amines as Y on the benzene ring if we want to run alkylation or acylation. Then lastly, just know that because of some oxidative properties of nitric acid, sulfuric acid mixtures, we can't use aniline as a starting reagent for nitration of the benzene ring because it'll just oxidize this to a nitro group. So just no substitution reaction will occur to make a nitrobenzene-like structure if we have an amine, NH2, and nitric acid and sulfuric acid. So it'll oxidize this. Not tertiary amines. If we take that and have alkylation, I guess 2 methyl groups here, that's fine. But if you have an amine or just a hydrogen and a methyl group here, you can start to have some oxidation reactions that we don't want. That's it for the substituent effects. Bye-bye.